All right, let's learn about earthquakes. So, what we'll try to cover in this little lecture here is we're going to kind of learn about the basics of earthquakes, and that would be, what is an earthquake? Where do they occur? Why do they occur? And then we'll talk a little bit about locating earthquakes, where the locations are, and then how to estimate the magnitude. So the damage or the energy, there's a couple different ways we can do that. So that's what we're going to work our way through for this little lecture. So here's kind of the little summary of what we're going to cover. So we will look at seismic waves also. Of course, those are very useful. And I've talked a little bit about seismic waves when we were looking at the interior of the Earth, if you recall. We learned a little bit about the energy that's released when an earthquake occurs and how that energy can move through the planet. And of course, we can use that to kind of see inside, a little kind of remote sensing, if you will, or some type of MRI kind of idea is how we kind of understood and see into the Earth so we can figure out what's happening there. And of course, they're helpful for locating earthquakes and estimating magnitudes and things like that. So, the idea behind an earthquake is there's the theory of the elastic rebound theory. So what does that mean? Well, what that means is that the place where there's some stress being applied. Now remember, you got to bring some of your knowledge from, previous lectures. There is the part of the Earth near the surface that is brittle. And so this is the part that breaks. And so what happens is we know about plate tectonics, this idea that these rigid pieces of the planet that are near the surface are broken up into these kind of plates, but that they are in motion, they are moving. And so ultimately they run into each other in some way. And so they might collide. We've talked about convergent plate boundaries, and we talked about plate tectonics, right? They could be ripped apart like a divergent plate boundary. They could even slide past each other. The idea is that they don't do this easily, right? So they're not slipping and sliding everywhere. It is difficult to push, pull, stretch, slide these rocks past each other or into each other. And so the initial thing that happens is stress is being built up in these very brittle pieces of the planet. But the idea is that they can store some of that energy. They can flex a little bit. Just because something's a solid doesn't mean it can't flex. If you can imagine like a meter stick, you can hold it in your hands, one on each end, and I can bend it to some degree. So it's a solid, it's brittle, but it has the ability to flex. What's it doing when it's flexing? Well, it's actually storing that energy that I'm imparting to the meter stick as I bend it. And the rocks are doing the same thing. So when there's a lot of stress being applied to the rocks, they actually bend a little bit. And so that bending or that deformation without breaking is where the rocks are storing that energy. But of course, these rocks only have a certain amount of strength, and so they can only store a certain amount of energy or stress. And once that's exceeded, what will happen is the rocks will break, and so that they will break in a brittle fashion. But they actually have been deformed, remember, so they're bent a little bit. Think of my meter stick, it's bent. When it fails, it snaps, or the rocks break, that meter stick rebounds back to its original shape. So if I take my meter stick, I bend it, it's flexed, it snaps. I don't have two bent pieces when I'm done. I have two straight pieces of wood, or, my little meter stick here. I have two pieces, and they're straight because the meter stick rebounded back to its original shape. And that rebounding back is the release of that energy. And of course, that energy propagates throughout the planet. This is the energy that moves away from the rupture, causes the ground to shake, and does some damage, right? So that's kind of the idea behind how energy is imparted into the rocks and it holds it, and then how it releases that energy to give us an earthquake. All right. And so, of course, there is some correlation here between the amount of stress we can store and the size of the earthquake, because the earthquake is related to the energy released. So if I can store lots of energy, a very strong rock per se, right? So we can store more energy. So maybe you could see that certain boundaries or certain rock types can lead to different size earthquakes. If we have rocks that are super strong and that can hold a lot of energy or stress, when they release it, it's bad. Or we have rocks that aren't very strong, so even though stress is applied, they fail maybe more often because they're weaker, so they can't store as much. So keep that in mind when we talk about earthquakes. All right, so the types of stresses that are being applied, and I'm sure we've mentioned this, but if we haven't, a quick little review here. We can squish the rocks. That's one type of stress. We can pull the rocks apart in tension, and we can shear the rocks, right? That's that kind of moving past each other. And of course, we can apply these stresses in a very general sense, of course, to the different types of plate boundaries we've discussed, right? So compression, we would see that where two plates are colliding. Hopefully that makes sense, right? They run into each other, we squish them, we have compression there, and that's one type of stress. We could also pull the plates apart. Now, one place we could see that happening is divergent plate boundaries, right? And so the stress is tension at that location. And then finally, we would have this shearing motion. Let me go back to that. There it is. And that's just where they're moving past each other. And so a place we see that is a transform boundary or a strike slip fault even. And so this is the places where shearing is happening, right? So you want to be able to, and like I said, this is a very general kind of story association, but it is true, right? Compression at convergent, tension at divergent, shear at transform. There are other stresses involved too at these locations, but these are the dominant stresses that we see. Okay, so when we look at deformation, we want to focus on this brittle type of deformation. So you can have rocks behave in a couple different ways. We're going to put them in two different categories here. The faulting, when we have an earthquake, we have a fault. This is where the rocks under stress actually fail and break in a brittle fashion. Rocks can also be deformed in a folding manner, what we call ductile. Now, we're really not going to focus on that because we're looking at hazards here, and we want to see that the hazards are associated with this release of energy that's abrupt, right? A brittle failure, releasing all this energy. But why would the rocks behave differently? You can see that the properties here kind of dictate how the rocks would behave when stress is involved. So the colder rocks, so these are the ones near the surface, tend to be more brittle. They're stronger. That means they can hold lots of energy, so they fail in a brittle fashion. And when we apply the stress quickly, right, over time, as opposed to a folded rock, and we usually see these at depth, right? So the heat is a big factor here. I got to allow the rocks to be a little more squishy, if you like, if they're weaker or if they have a slower strain rate. So I apply stress, but it's very slow over a long period of time. The rocks can actually compress and fold. But like I said, heat is a big driver here, right? We don't want them to break in a brittle fashion. They actually fold like that. But for our purposes, when we talk about earthquakes, we're going to focus on this brittle failure here, right? That's kind of what we want to look at. Okay, so a couple things we're pulling from the past again, right, is that when we talked about sedimentary rocks briefly, we said that, we deposit these rocks in a layered fashion. And we talked a little bit about bedding and what that meant. And so one of the rules of sedimentary rocks is that in general, they're deposited horizontally. And so that can help us when we look at earthquakes, because a lot of times when there's a brittle failure, there's this stress, the rocks break and are shifted. And so when we see bedding that is not horizontal, it can give us an indication that maybe an earthquake occurred here or there's a fault nearby, but certainly that there was some stress applied in this area. And so we can use that to help us kind of figure out what's happening here. Or, like I said, look at past earthquakes. And so as you're driving around and you see rocks tilted, you want to think, oh crap, there's something happening here. There was some stress applied here. There must be some faulting here. And then, of course, we could try to identify where those faults are. Because, of course, if they're active faults, then we want to be aware and be prepared for that. So what we're going to focus on for the next few minutes here is these faults. And so one of the things that's kind of useful is to determine what type of fault we have. So there's 3 different fault types that we're going to talk about. And the thing that's useful about that is specific stresses usually generate specific faults. And so that can be useful when we talk about, why are the rocks breaking here? Is it tension? Are the rocks being pulled apart here? Is it compression? Are they being squished together? Or are they being sheared? And so what we want to do is, the first step, of course, is to identify a fault. So what is a fault? Well, it is this fracture, this break in the rock, but it's not just that there's been a breakage. In order to be identified as a fault, we need motion, movement along that breakage. So if it's just a break, it's just a crack in the rock, or maybe we would call it a joint. And so that is where the rock has failed. It is broken for a variety of reasons. But if we can identify that across that breakage there has been some motion, we would interpret that as a fault. And so in this picture here, what we're using is the layering here. We're arguing that the layers are not matched across this breakage here. And if we can restore them to their original position, then we can determine motion along the fault. Did the left side of this block slip down? Did the right side move up? And so we're going to use that to help us figure out whether there's been some tension or some compression or some shear on this fault here, to interpret what it is, its name, and the type of stresses that are involved here. All right. So the first thing, of course, is to find the fault plane, and then we want to figure out motion. Did it move, up or down, kind of thing? And let's see if we can make that a little clearer. All right. So here's an image here. So we have this break here. So we can determine that there has been motion along this breakage. So instead of calling it just a crack, a fracture, or a joint, we're going to say this is a fault because I can identify motion. And I'm doing that, right, because we're assuming that this black layer here was laterally continuous, right, that it matched up. It was nice and straight. But since that time that it's been deposited, it has been broken and there has been some motion. And so we want to identify the fault plane. And so we can do that by just drawing a line. So this is where the breakage occurred. Now the trick here is to figure out which way the blocks have moved. Now, this is challenging. I mean, initially it's not challenging. You'd be like, okay, I can see that this top or right part looks like it went up. Okay, and I would agree with that. Or you could say, but the bottom part went down. Okay, I could see that too. So did this right upper here move up, or did this go down? Or was it a little bit of both? The problem is we can't tell because we didn't see it move. And so it could have been one of those 3 things. The block up here moved up, the block here moved down, or a little bit of both. And so to eliminate that kind of confusion, we want to set some kind of rules about how we identify motion so that everybody is in agreement. Okay, this is what we're going to say, and this leads to how we identify these. Now, this other thing that I want to throw out at you is this view that we're looking at. This is what we're calling a cross-section view, cross-section, right? We're cutting, think of a cake. So if have our nice, beautiful cake and we're looking down on the surface of our cake that has written happy birthday on it, that it was a map view, right? Like if you're in an airplane and you're looking down on the surface of the earth, you're seeing the surface. But that's not what we're seeing here, right? We have cut into the cake and looked at the layers in the cake. So that's a side view. Okay, so that's important because the 3 faults that we're going to identify, 2 of them, we need a side view, a cross-section view. Okay, and the third one is identified from that map view where we're looking down from our airplane. So what we're doing here is we're looking at a side view, a cross-section view. And we want to differentiate between 2 different types of faults that can be identified by looking at the rocks in this view. So how do we know up, down, right, left? So the rule is that we really want to identify this block, okay? And we're going to give it a name. We're going to say that this block that is above the fault plane is called the hanging wall, okay? And so how do I know it's above the fault plane? Well, the simple trick would be that when there's a breakage like this and you're looking at a side view, right, a cross-sectional view, if you can put your finger or your pointer or your pencil on the fault plane and then draw a line straight up, right, vertically up from that point, you will be in the hanging wall no matter where you place your little pointer or finger, right? And that's always true. So move up, I'm in the hanging wall. What we want to do is say, what did the hanging wall do relative to the block that's below it here, which we do give a name to. We're going to call that the footwall. But the rule is we only care about what's happened to this piece up here, this hanging wall. Did it go up or down relative to this block here? So because they were once together, the horizontal line, the way that it got offset like this with this block, the hanging wall, would have had to move up. Okay? And that's what we're going to say happened, that this hanging wall moved up. So in order to differentiate between the two different types of faults that we can identify from a side view, cross-section view, when the hanging wall goes up, we're going to call this a reverse fault. And when the hanging wall goes down, we're going to call it a normal fault. Okay, and so these are the two different types of faults that we want to identify when we're looking at a cross-section view. Okay, so if we were to look at, let's say, a block diagram, let's look at something like this. What we're seeing here is a line that we can identify as the fault plane. Which one is the hanging wall? Well, remember, we just put our cursor, finger, pencil on this line and go straight up. That means in this example, the hanging wall is the block on the left, right? That's correct. I should use that term. It's the hanging wall is on the left. Correct. Okay. What did it do? Well, let's make these layers match up. So before anything happened, this layer was down here along this, and it was a nice continuous layer. In order to get it to this current state, I would have had to have moved the hanging wall up. By definition, this is called a reverse fault. Okay, and so this is the official way to identify, reverse faults, and the other one called a normal fault. So you'd have to kind of memorize that. Hanging wall up, reverse, hanging wall down, normal. Sometimes I think about it as, because this block here, which is the foot wall, kind of looks like a slide, and this block is kind of resting on the slide. For me, if the hanging wall goes up the slide, that's not normal. So that's reverse of normal. So that's a reverse. But if this block kind of falls down the slide, slips down the surface, that seems normal to me, because that's what you do on a slide. That's a normal fault. You can use that little method to determine normal and reverse, if that works for you, of course. And so the other thing we want to associate with this type of fault is that compression is causing this type of fault. When we crush the rocks, we tend to get what are called reverse faults, where we push the hanging wall up the slide. Okay, so when we talk about reverse faults, we want to associate that with compression, right? And so this is important, because then we could say, oh, we have reverse faults, we probably have compression here. Maybe that can even lead us to some interpretation about a boundary that might exist here. But knowing the stress, then we can kind of figure out where's the stress coming from and all those kind of good things. So the second type of fault that we can identify from a cross-sectional view, remember, we need a side view in order to identify these two faults. We need to look at the layers of the cake. In this case, where is the hanging wall? Here's our fault plane. It's this line here. I put my cursor finger, I go straight up. Now I'm in the hanging wall. What did the hanging wall do? Well, it was up here lined up, and then it had to go down in order to get to this current configuration. And so down the slide, that's a normal thing to do. We're going to call that a normal fault. And normal faults are typically caused by tensional stresses. We're trying to stretch the crust, right? Both of these are stress. Both of these are causing the rocks to deform and then finally fail, catastrophically releasing energy, okay? And so when you're asked to identify faults, and I think the homework this week asks you to do that, you're going to have these block diagrams. Remember, the view is important. In order to identify these type of what we call dip slip faults, these are ones that have some type of vertical. The major motion on these faults is vertical motion. That we need a side view to see that it's moved up or down. And so once you have that side view, you identify the fault plane and you figure out did the hanging wall go up or down, and then you know which type of fault you have and then which type of stress you have. Okay? All right. The third type of fault we want to look at is what's called a strike slip fault. This is our shear stress type one, right? The good news is for us, we're just going to identify there's just one type. It's a strike slip. It just means that there's some type of shear happening here. What we need for this one, though, because it's horizontal, right? There's not a lot of up and down motion. We need a map view. We need to look down on the surface of the earth, and we still need a feature that we can see has been offset. Because once again, just a crack in the rock without motion is just a fracture or a joint or a crack, right? But we need motion to determine that it's actually a fault. And so a lot of times when we're looking in the middle of nowhere, we're looking for features like a river. And so this example to the right is showing that a stream has been carved into this sediment here, and it makes this really sharp turn along this feature here, suggesting that it's been moved, okay? And so that would indicate a strike slip fault, and the stress that we would associate with that would be shear. And once again, we would need a map view to determine this. We couldn't really determine it from a cross-section, the layer cake, because there's no up and down motion. Okay, so it's key that when you're trying to identify a fault, now of course in a classroom setting where we have to draw you pictures or give you block diagrams, the view is important. If you're out in the field, of course, that might be a little different, but for identifying faults from little diagrams, you need to know what view you're seeing. Are you looking down on the surface of the earth, or are you looking at a cross-sectional view? Okay, here's a few more pictures. You can see this one's more dramatic, right? So that's the river, channel that's been carved, and that, what happened? Okay, that suggests, and we're in our plane, looking down on the surface of the earth, that there's been some horizontal motion. And that suggests we have a strike slip fault, and that suggests that shear stress is causing that to move like that. Okay, this is a part of the San Andreas fault here. All right, what else we got for you? You can see the offset in the stream there, and then we can see the motion. All right, and this is the San Andreas fault is a big fault system, right? It's not just one fault. But a lot of times it's just referred to as the San Andreas fault, but it's basically a big system of strike slip faults. And it is related to the boundary between two plates. Not all strike slip faults do that, but here there is a big fault system that runs through California like this. On the right-hand side is the North American plate. On the left-hand side is the Pacific plate. So this is a fault. It is mainly along this whole area here a strike slip fault. And because it's a plate boundary, it's a transform boundary. So it's got all those things. And of course, it's shearing. The general motion here is shear stress as it's moving like this. Now, of course, in the gritty details, we have multiple faults, and it's not just one little line. You could kind of walk the entire length and identified as, the San Andreas Fault, right? So lots of little systems here that are interconnected and little splays. Oh, great, crazy, right? But let's not get into that too bad. Okay, a couple kind of weird ones we'll throw at you because you might read this terminology here. So what we're seeing here, look, we can identify this as now this angle of the breakage is different from what you've seen in the previous diagrams. It still works, right? So if I take my finger, pointer, pencil, put it on the fault plane and go straight up, this is the hanging wall. What did the hanging wall do? Well, it was lined up with this brown layer. It went up the slide. That's not normal. This is a reverse fault. True. It is associated with compression. True. But a lot of times it's referred to as what's called a thrust fault. So when you get these low angle kind of compressional faults like this, we call them thrust faults. For us, reverse faults, those are interchangeable for us because it is a reverse fault. Okay, so we can get those types of features. Still got our hanging wall, footwall kind of story, right? So we can still figure it out. And then the other thing I just want to mention is I referred to the first two, normal and reverse, as what are called dip slip faults, where there's mostly vertical motion. We've identified a strike slip fault, which for us there's just one, just a strike slip, right? That's horizontal. But of course, look, in the real world, when there's a fault and a lot of energy is released and there's motion, there's probably a combination of both horizontal and vertical, and we would give it a name of oblique slip. But look, in a place where there's a lot of shear stress, we would get a strike slip fault. Does that mean there's absolutely no vertical motion? Probably not, but the majority of the motion is horizontal. So we would identify that as a strike slip fault. When we have a normal or reverse fault, is 100% of the movement vertical? Well, probably not, but a majority is, right? 90% of the motion is accommodated by a vertical movement, and there might be a little horizontal. So we'd still classify that as either a normal or reverse, depending on where the hanging wall was, up or down, right? So just wanted you to be aware of how that works. What else? And then just to give you an example of kind of what we see in Arizona here, if you happen to be from Arizona, South Mountain is a place, a park. It's actually a big city park. And Papago Park is the little kind of reddish buttes that are across from the Phoenix Zoo there. And so what we're seeing here is it's a little more complicated, of course, in the real world. But look, this is the main fault here. And so we could say that, above it is the hanging wall. These blocks have actually been pulled apart. And so our hanging wall in this case has broken into multiple pieces. And so it's actually, if we look at these two, this and this were lined up. This went down this slide. That's normal too. So a big normal fault and a bunch of normal faults here. What you're seeing at Papago Buttes is just the tip of these broken tilted blocks. These are the red rocks that stick out at Papago Park. And this is some igneous rocks, some metamorphic rocks. Where were they? They were deep in the earth down here, but they've been pulled out. Erosion has removed a lot of material, and now they're exposed at the surface. And so this is one way that we get granites, big kind of igneous intrusions that have cooled and crystallized at depth. Metamorphic rocks that usually form at depth. How do they come to the surface? This is one way we can do that. And so there's been a lot of tension. So the crust is really being pulled apart here, and we get these very weird kind of faults that kind of give us some of the geography that we see in Arizona. All right. We won't worry about that one for us. We'll pretend that didn't happen, and we'll move on with that. So you don't have to worry about detachment faults, right? So that was just an example to show you, what we can see here in Arizona. And of course that it gets complicated, but we're not going too crazy complicated. You are just required to identify normal, reverse, and strike slip faults and the associated stress that's, applied to each one and why they occur. And so As a quick review, remember, we've got these plates. And how did we identify the plates? Well, where they came into contact with each other, right? And so the collision of plates, whether that's coming together, pulled apart, sliding past, is defined by high stress, which is then defined by earthquakes. And so we can plot earthquakes, and it basically outlines a lot of the major plates that we see that make up the surface of our planet. And the different types are here, right? You can see they use thrust faults in this diagram. Remember, for us, that's a reverse fault, so don't let that throw you. And there are some terms that we'll talk about here in just a second, but epicenter and focus we want to be aware of. So just reminding you of the relationship, right, between plates, plate boundaries, and earthquakes, okay? What else I got? Okay, so let's move into where earthquakes are. So we know in general that earthquakes are occurring at these plate boundaries where the stress is high. But how do we determine where an earthquake is? So the terms that we use to describe earthquake locations are the focus and the epicenter. So the focus is the location where the rupture first initiates. So when the rocks finally fail, there's motion, it initiates somewhere at depth, and then that can propagate horizontally and vertically along this contact between these two blocks. The epicenter is just a surface location. So once this is determined, the focus, we can just draw a line straight up. And wherever it intersects the surface of the earth, we would say, hey, that's the epicenter. Because no one, hey, there's an earthquake and it occurred 25 miles inside the earth. It's like, okay, great. But where? So we want to know the surface location. Oh, it happened in Napa Valley, or it happened in LA, or it happened in, wherever city, town that's closest to that location. We want to tell people, hey, there was an earthquake and this is where it was located. So that's why we have the epicenter, right? Okay, so let's talk a little bit about seismic waves. So like I said, we talked about those when we did interior of the earth, and same thing. We're not going to get crazy detailed into this, but we should know some of the basic waves that are generated when an earthquake occurs. And so there are body waves, waves that actually propagate through the interior of the earth, inside the earth. These are the ones we looked at when we were trying to figure out what was happening inside the earth. So P waves, primary waves, S waves, secondary waves. There's also surface waves that we'll talk about in just a minute. But each of these body waves, the P and the S wave, have some properties that are important. And so if we look at those, what we see is the primary wave is the fastest wave that we see. Okay, and so this wave, when there's a rupture, it's a compressional wave. And so the energy is moving out kind of like, it's not, wish I could show you in person, but kind of like how a slinky behaves when we squish it together. So if we stretched out a slinky and then we pushed it together, we compress the springs here. What happens is the springs impart that compression all along the slinky here. And that's how the energy is transmitted along the slinky. The rocks are doing something similar, okay? So the rocks are being compressed. Yeah, they're not being squished like, a piece of clay, because they're rebounding, remember? But we're squishing them and it's imparting energy. It's a very fast way, an efficient way to make energy go through an object, and so this is why it's really fast. It can move through solids and liquids, and so we see that and we can record that on our seismometers. The second thing that we see is what's called a S wave, shear wave, secondary wave. I'll take any of those names for our second body wave. It transmits its energy through this more of a shearing motion. And so the example would be kind of this rope here. We kind of do an up and down motion with our hand, and the rope kind of moves in that up and down motion all along the rope, propagating the energy along the rope. Rocks are doing the same thing. They're flexing in this kind of up and down or side to side motion. So it's this shearing. It's not as efficient as our compression, so it's a little slower. And as we've learned from before, it can only move through solids. So we can record both of these P waves and S waves, and because they're different speeds, we see them come in at different times. That is useful for us in helping us determine where an earthquake epicenter is, of course, okay? The two other waves that we'll kind of mention briefly are what are called surface waves. Those are a Love wave and a Raleigh wave. These are the slowest moving waves that we see, and because of that, they cause the most damage. They run along the surface instead of penetrating deep into the earth. They cause the Earth's surface to move both vertically, kind of in a rolling motion, and horizontally in a shifting side-to-side motion. And like I said, the slow movement, as something moves really fast, like bam, it's through and gone, right? You're like, holy cow, what was that? It didn't do much damage because it moved super quick. But if this thing comes through super slow and is rocking things back and forth, this is why it causes more damage than the P or the S wave, because they're so fast relative to these surface waves, and because the surface waves are kind of confined to the surface, right? They're expending more energy near the surface. So how does this help us? Okay, finally we get to our seismograph here, okay? So this is a machine that we can use to record the energy waves, and then of course for us, we can use that to figure out not only the magnitude, but the location. So right now we're driving for location. We want to know where this earthquake occurred. And so it looks something like, today, of course, it's all done by computer, so it's a digital readout. But you can have drums, like rolling drums, where there's a paper and a pen, and it would actually record on there. But these are some examples of what we might see, right? These kind of squiggles up and down are indication of ground motion or shaking. And of course, because we know something about the speed of waves, we can figure out which wave might be which. So let's look at that. So here's an example of our dreaded seismogram. So this is the paper / digital kind of readout. So we're happily going along, and these lines indicate time. So it's just kind of moving along, and there's no vibrations. And then we kind of see an initial blip. And so because we know when an earthquake occurs, the first thing I should record, because it's the fastest, is the P wave. And so I get this blip of kind of shaking. We're going to assume it's the P wave. And then the next thing that should show up, because it's the next fastest, is the shear wave, the secondary wave. And then because our surface waves are the slowest, those are the ones that come in third. And of course, they usually, like we're seeing here, shake the ground the most because they're slow and they're near surface, okay? What we want to be able to do is use the arrival time, the difference between when this P wave arrived at my station and this one, to figure out where the earthquake occurred. Because if I know the speeds, the speed of the P wave and the speed of the S wave, the difference can tell me how far away the earthquake was from my station. Now, we would need some charts here that were developed for the types of rocks that are exposed, and some knowledge that we have about the speed of the P and the S wave. But what we would do is we would take that, what we're calling lag time, the time difference between these arrivals, we would take it to our chart and apply it. And what this is trying to show you here is at this location here, the time difference. So this chart would be this, and it would have these kind of, what color are those? Blue, green kind of lines on there. And the idea is that between this line and this line is the lag time. So I would take my seismogram and I would line it up so that it fits. So I would move it up and down until it fit, right? It fits right here. And so that would mean that I'm about, 275 kilometers away from the epicenter. And then I would take another station, because they're a different distance away, in this case farther, their lag time is bigger. And so I would move it down this chart until it fit between these two lines. And then I'd go across and say, oh, I must be 475 kilometers away. And then we would need at least one more to triangulate to figure out where the earthquake occurred. And so this last one would give us another distance. Maybe that's 775 kilometers away. And so then all we would do is we would make a circle around each of the 3 stations. And so for this example, the Memphis station, all I know is distance. I don't know direction. And so if it's 275 kilometers away, well, I guess they're telling me 261. I'm not a good guesser. Okay, so 261, I would take a little compass here and I would draw a circle with a radius of 261 kilometers. And what that tells me is somewhere on this circle, the earthquake occurred. Because I know distance, I just don't know direction. So I need another one. We take the Indianapolis one. Where's that at? That's here. So that one says it's 464, I think. And so we do the same thing. We draw a circle around and say, oh, okay, I need a third one. We draw our Des Moines. Where they all intersect, this would be the epicenter. Right? So I need at least 3 stations to accurately locate the epicenter. Now, of course, today we can find those things instantly, right? So we get computers that are, showing that there's ground motion. They're evaluating those, they're communicating, and bam, within seconds I can find the epicenter. Back in the day, of course, you're calling people and drawing on maps and all that kind of stuff. But the process is still the same. It's just faster today. And so this is how we would determine the epicenter, the location, okay? So we need seismograms, which is the printout or the electronic kind of signature of the earthquake. We would need to figure out the lag time between the P wave, the fastest, and the S wave, the next fastest, and use our chart. We line it up, it gives us a distance away. If we have 3 of those, we can triangulate and find the exact place that it occurred. The epicenter, this is the surface location of where the rupture occurred somewhere at depth, okay? Oh golly, okay. Last thing we're going to discuss in this little lecture about earthquakes is the magnitude. So there's a couple ways to measure the magnitude of earthquakes. The one you've probably heard or most familiar with is called the Richter scale. And so it's measuring kind of intensity. Probably a better way to think about it is the energy released from the earthquake. And so it was actually started by a guy named Richter, and he was evaluating California earthquakes and using a seismogram, the printout of a earthquake trace here. And what he was using was how tall, how high this S wave was. And as he collected a bunch of evidence, what he was able to do is kind of come up with a formula that related the size of the S wave, this amplitude, this height, to kind of the amount of energy that was released during an earthquake. And so we don't need formulas or anything like that, but what you want to be aware of for the Richter scale and even the scale that we're currently using. So look, the Richter scale was effective for California smaller earthquakes. As it was expanded worldwide, they noticed that there were some kind of flaws, kind of some issues with that. So what they do is they kind of modified it. And it's still kind of similar, and they can still figure out the intensity / energy released. And it's still logarithmic, but it's kind of called the moment magnitude scale. But for us, what we want to be aware of is the scale that we're seeing on the news and things like that. That's a lot of times referred to as the Richter scale, but it might just be, hey, the magnitude of that earthquake was a 7.2. What we want to know is that because it is logarithmic, so for every whole number on this magnitude scale that we're using, there's a 30 times energy increase. So this is why it's important when you're identifying magnitudes that you know the difference between, was it a 7.2 or was it a 7.7, right? Because it doesn't seem like much, it's 0.5 difference there. But because one whole number is 30 times, half of that, 0.5, that's 15 times more energy. That's a lot. And so it's important to understand that, right? So when we look at energy released during an earthquake and we're measuring that with our kind of magnitude scale that's logarithmic, there's a 30 times energy release between one whole number. So think about that. If we have a 5 and then a 6, the difference is 30 times more energy. But what about the difference between a 5 and a 7? So the 5 to the 6 is 30 times, and the 6 to the 7 is 30 times. So 30 times 30, 900 times. So the difference between a 5 magnitude and a 7 magnitude is 900 times more energy released during that 7 than that 5. That's a lot. Okay? And so we want to be aware of this huge amount of energy released. And, let's see, I don't know how useful this is per se, but I'll still show it to you. And so this little chart is telling you the energy released relative to the magnitude. Okay, and so it's listing some issues that we would have during these different magnitudes, different examples, and then some things you might have heard of, seen, whatever, that relate to energy equivalents, right? So a lightning strike, the energy released in a lightning strike might be the energy released in like a 2.2 magnitude. A tornado may be like a 4.5. And so then we get into atomic bombs and other things, like that. And of course, kilograms of explosives, I'm not sure how useful that is. It just shows the progression, how fast it would increase the amount of energy that's released. And of course, it's also showing us that big earthquakes are not as common and small earthquakes are super common. But, the energy released for this type of scale is important. So the other scales, I'm sorry, let me go back. Here's that one, the seismic moment magnitude scale is kind of what we use today. It's a lot of times what you'll hear on the news is there was an earthquake and it was a, 6.5. But then a couple, hours later, it'll be readjusted to a 6.7 or 6.4. And even some places will call it one thing and another. They'll be within usually like, 0.2 or 0.3. But as time goes on, we can get more data, then we can get a more accurate evaluation of the magnitude as we can figure out the energy that was released. Because in some cases, we need more information, right? So we need, how much of the area ruptured and all those kind of things, and strength of the rock. And these things also give us more information so we can determine a more accurate magnitude. The other scale that was just listed there is called the modified Mercalli scale. It's really measuring damage, and it was kind of developed early on where people were using eyewitness accounts to evaluate kind of what happened during an earthquake. It's still kind of used today. The USGS actually still uses this. If you go to their site after an earthquake, a lot of times you'll see a little map like this that's showing ground shaking, kind of the intensity. And so in order to kind of alleviate some confusion, the Mercalli scale, or the modified Mercalli scale, uses Roman numerals. And so 1 being the smallest amount of damage and 12 being, oh my goodness, everything's, flattened. And so it can be a little subjective, and there's a lot of factors that kind of indicate whether, there's damage or not, right? So at certain locations, rock type and things like that, and your experience if you're interviewing people can kind of make it not as accurate. So we want to be a little careful with that, because anybody can be interviewed for that, especially today. You can go on the USGS site and say, hey, I was in that earthquake. I was at this location, and this is what I think happened. This is what I saw happen. Back in the day when they used this scale, they would try to, pick people they felt were reliable and ask them, hey, what was your experience? And they gather that information and they kind of come up with a map, kind of like this one, that would say, look, if you were in this area, you experienced a pretty high damage and ground shaking, and the farther away, less. That seems logical, and that's usually what happens during earthquakes. But this irregular shape can be indicating of different rock types or building strength or things like that, or even someone's experience. Because of course, if you've been in, 10 earthquakes and there's an earthquake, you might not be so upset about it. And you'd be like, it wasn't too bad, not a whole lot of damage. If you've never been in an earthquake, it could be the most crazy thing you've ever experienced, and you might over exaggerate some of the damage. And this ultimately could, make it not as accurate, right? So we want to be aware of that. And the last thing I'll show you is this is the scale, though it's been modified a little bit. And so this is the intensity scale. And so you can see by the descriptions here, it's really describing damage. And so we're looking more about, for the Mercalli scale, damage, and for the kind of Richter scale, moment magnitude scale, we're looking for energy released, right? How intense that was. And so you can read through these if you so choose. I think in the lab, I asked you to actually kind of go through and identify some of these. But it goes all the way up to 12. Almost everything is destroyed. Objects thrown in the air, right? All that kind of stuff. And they're equating that with something greater than an 8 magnitude on the Richter scale. So if, there was an earthquake and we were trying to do the modified or the Mercalli scale, you would be interviewed. And then me as the evaluator would try to be like, okay, where does that fall on these descriptions? It's, kind of this one I like, for what you describe to me of your experience, and I'll say, oh, that must have been an 8 at this location. And of course, the more data we can gather, the more accurate we can be with that. But that's kind of how that works for our magnitude scales. Okay, so I think we made it through this lecture. I know it's long, so what you want to remember from this lecture in the PowerPoint, right, is where they occur, why they occur, the different types of boundaries and the different types of faults, the stresses that are related to those faults, and potentially what boundaries we would tend to see those at, right? Because we know stress is related to boundaries related to faults. We can kind of interconnect all those. And then to be able to understand how we can figure out location, right? We need a seismograph, and we need the seismogram, the little printout. We need P and S waves. We need lag time, right? We're using 3 of those to get a location. And then there's a couple different magnitude scales. For us, Richter moment magnitude, even though they shouldn't be used interchangeable, for us, we're just going to use that as our magnitude number, right? Our 7.2 that you hear on the news, your 8.3 that you hear on the news. And so those are the ones that we're going to look at for energy, how much energy was released during that event. And then the Mercalli scale is something that we're using to kind of talk about damage, what happened on the ground, right? Something we can describe. Okay. All right. Hopefully that gets you some background so that we can then talk about some of the hazards that are associated with earthquakes.